within the Jinping Mountains of Sichuan, China.
Hidden beneath 2,400 meters of solid rock is the world's deepest underground laboratory. This is the story of how China constructed the CJPL project, an impervious fortress for dark matter detection. The journey begins 17 kilometers deep inside the Earth, utilizing access tunnels originally dug for a hydropower plant. In 2020, the second phase, CJPL-2, officially began.
Engineers utilized advanced building information modeling to map every inch of the rock structure before digging.
The first step is excavation. Specialized drilling jumbos are brought in to pierce the incredibly hard marble rock.
The rock here is marble, which provides excellent radiation shielding, but presents immense geotechnical challenges.
Controlled blasting is used to carve out 4 massive experimental halls, each 14 meters wide and 130 meters long.
The blast fractures the rock, inching the laboratory deeper into the mountain. Massive ventilation systems immediately purge the air, removing dust and dangerous radon gas.
Excavators work tirelessly to remove the debris, clearing the space for the new experimental halls.
Thousands of tons of rock are transported out, a continuous conveyor belt of heavy machinery.
Once the rock is cleared, the walls must be stabilized immediately to prevent rock bursts. Steel rock bolts are driven meters deep into the tunnel roof to anchor the unstable rock layers.
These bolts act as the skeleton, holding the mountain's immense pressure at bay. A layer of shotcrete is sprayed over the bolts, sealing the loose rock and creating the initial shell. At this depth, high-pressure groundwater is a constant enemy. Waterproofing is the most critical phase. The team implements a sophisticated water-resistant and radon suppression, or WRRS system. The first layer of defense is nano-modified steel fiber concrete, designed to resist micro-cracking.
These tine steel fibers strengthen the concrete, allowing it to withstand the immense hydrostatic pressure.
Next, a layer of HDPE dimpled drainage board is installed against the concrete. This board creates a cavity, allowing seeping water to drain away rather than entering the laboratory.
Every seam is heat welded to ensure a perfect, watertight seal.
The hall begins to take shape, transforming from a jagged cave into a structured tunnel.
To block deadly radon gas, a layer of rapid-setting liquid rubber is applied. This liquid rubber hardens instantly, forming an elastic, gas-tight membrane.
It seals every crack and crevice, preventing radioactive gas from interfering with the sensitive experiments.
A steel rebar cage is constructed to support the final inner concrete lining.
The structure must be rigid enough to support heavy equipment and shielding plates. Polymer cement concrete is poured to create the smooth, final interior walls. Vibration removes air pockets, ensuring a dense, radiation-proof barrier.
As the concrete cures, the cavern becomes a clean, dust-free environment.
The floor is leveled to ultra-precise standards to support sensitive dark matter detectors.
Even a millimeter of deviation is unacceptable for the equipment that will be installed here. Another layer of polyurethane cement is added for durability and thermal insulation.
The final white coat reflects light and seals the surface, creating a laboratory-grade finish.
The rough cave is gone. It is now a sterile, high-tech facility, deep underground. To maintain air quality, A dedicated fresh air system is installed.
This system pumps fresh air from the surface 17 kilometers away through a network of ducts. The air pressure inside is kept positive to push radon gas out of the laboratory.
Lighting is crucial. High-intensity LEDs mimic daylight to keep workers alert in the eternal darkness.
Now, the most unique construction phase begins: the installation of the polyethylene shielding.
Over 1,800 tons of polyethylene are used to shield the experiments from background neutrons.
These plates are custom manufactured to fit together like a giant 3D puzzle. The goal is to install them without continuous joints, preventing radiation leakage.
Precision is key. A gap of even a fraction of an inch could ruin an experiment.
This creates a room within a room, the quietest place in the universe for radiation. Access is strictly controlled to maintain the ultra-low background environment.
For the Panda X experiment, a massive water shielding tank is required.
A pit 13 meters deep is dug and reinforced to hold thousands of tons of ultra-pure water. This tank will surround the detector, using water as an additional shield against radiation. The liner ensures that the ultra-pure water remains uncontaminated by the concrete. Complex piping systems are installed to circulate and purify the water continuously. The components for the liquid nitrogen cooling systems arrive at the site. Dark matter detectors must be cooled to cryogenic temperatures to function. Specialized welders ensure the cryogenic lines are leak-proof under extreme cold. Every weld is inspected with X-ray technology. Failure here is not an option. Heavy-duty overhead cranes are installed to lift the massive detectors into the tanks. These cranes are capable of lifting up to 50 tons with millimeter precision. Miles of cabling are laid to power the facility and transmit data. Power interruptions could destroy years of data, so redundant generators are essential.
Safety systems, including advanced fire suppression, are integrated throughout the tunnels.
High-speed internet connects this remote cave to universities and research centers globally. As construction winds down, the focus shifts to cleanliness. The site must be spotless. Anyone entering the clean zones must pass through air showers to remove dust. The heart of the project, the detectors for Pandax and CDX, finally arrive. From this point on, workers must wear full cleanroom suits to prevent contamination. The detectors are built with ultra-pure copper, mined and processed to be radiation-free. The assembly is a delicate process, requiring patience and steady hands. The detector is slowly lowered into the water tank, the final layer of its protective cocoon. Submerged in pure water, it is shielded from the cosmic noise that bombards the surface. The tank is sealed. The physical construction is complete. The scientific phase begins. It takes days to fill the massive tank with ultra-pure water. The control room becomes the brain of the operation, monitoring every sensor. Systems are brought online one by one. Cooling, circulation, data acquisition. The ventilation system hums, maintaining a constant temperature and pressure.
Radon levels are checked constantly. The air here is now purer than anywhere on Earth.
Liquid xenon, the target material for the Panda X experiment, is delivered. The xenon is pumped into the detector, where it will wait for a collision with dark matter. Hall B is now fully operational, housing multiple experiments simultaneously.
CJPL-2 has capacity for thousands of researchers, becoming a global hub for physics. The data collected here is massive, requiring on-site server farms to process.
Maintenance crews work around the clock to ensure the facility never stops running. While the world sleeps, the hunt for the invisible universe continues deep underground.
Every spike in the data could be the discovery that changes physics forever.
The expansion to 300,000 cubic meters makes this the largest underground lab in the world.
Even sound vibrations are minimized to create the most stable environment possible.
The horizontal access allows large trucks to drive delicate equipment directly to the lab.
The CDEX experiment uses germanium crystals to hunt for lighter dark matter particles. These crystals are incredibly sensitive and must be handled with extreme care.
Liquid nitrogen keeps the germanium crystals at their operating temperature.
Another experiment, JUNA, recreates the nuclear reactions that happen inside stars. Here, they study how stars create elements, safe from cosmic ray interference. Every experiment is monitored visually to ensure physical integrity. Cleanliness is a never-ending task. Dust is the enemy of dark matter detection.
Air filters are changed regularly to maintain the Class 10,000 cleanroom standard. Scientists from Tsinghua University and Yalong River Hydropower plan future upgrades.
Safety protocols are rehearsed rigorously. The tunnel provides a quick escape if needed.
The scale of the facility is breathtaking. A city of science buried in the mountain. CJPL stands as a testament to China's commitment to fundamental science. The silence here allows them to hear the faintest whispers of the universe. As the lab reaches full operation, the last of the heavy construction gear is removed. The heavy lifting is done. The intellectual heavy lifting now begins.
Phase 2, or DURF, was completed in December 2023, on time and on budget. Security is tight. Only authorized personnel can access the core detector areas.
The water purity is maintained at 18 megohms, the theoretical limit of purity. With experiments running 24/7, researchers often live underground for days. 2,400 meters of rock, the deepest shield of any lab on the planet. Regular inspections ensure the shielding remains perfectly intact over the years. They are waiting for a WIMP, a weakly interacting massive particle, to strike. The background noise here is 100 millionth of that on the surface.
Every successful test brings them one step closer to unlocking the mysteries of the cosmos.
From a hydropower tunnel to a world-class laboratory, the transformation is complete. This facility will serve as a key research hub for the next 30 years. Not just physics, but biology and geology research will also find a home here. We leave the scientists to their work, isolated in their fortress of silence. Returning to the surface, we realize the magnitude of what lies beneath.
The China Jinping Underground Laboratory, looking deep into the earth to see the stars.